The final section of this unit is going to expand on the number of rules and tools that we have in our little toolbox to justify our thinking. So we're going to get some more geometric things. Last section we played with the algebra tools we were familiar with. So we had some familiarity with the tools. The justifying was new. Now we're going to expand and we're going to add some new tools specific to geometry. So we're thinking about how pictures and shapes are related. And we're going to still use those algebraic tools because, again, we're always going to be wanting to move words and pictures into equations. Because once I have an equation, bam, I've got all of my algebra tools at my hands to solve for things. So here we go. We are, after this lesson, using definitions and theorems to justify your thinking. You're going to provide that step-by-step justification of why something must be true. It's like mathematical lawyers. It must be true beyond a shadow of a doubt. Cannot argue it. No other choice is possible. So, super powerful stuff. First one that we use a lot is part to whole. And this one should just feel really, really good in your gut. It says, for any segment or angle, the sum of the parts equal the whole. If you think about a pair of adjacent angles, if you take the two angles, they have to equal the bigger one. Okay, that's really what this is saying. So I'm going to show you some pictures. If I had a segment like this, we'll say A, B, and C. Parts to whole says AB, little piece AB, plus piece BC, non-overlapping pieces, has to be equal to AC. Really take a minute and think about that. That this piece plus this piece has to be the whole thing. And that should feel super, super comfortable. That makes sense. Totally logical. You have a big thing, you cut it into two pieces, the two pieces still have to equal the big thing. Same thing works for angles. Now, I don't know how those two pieces are related. If they're half, if they're a third, if they're a quarter, whatever. I just know that if I have the two of them and I put them back together, I get the whole thing. All right, so I have this set of angles here. What I know is that angle WXY, this one, plus angle YXZ, this one, has to equal the whole thing, angle WXZ. And this is why naming is so important. This piece plus this piece has to equal the whole thing. When you write that equation, so this is going to be where you're going to have a picture, and you can write an equation from the picture. Your reason for being able to write that addition number sentence that they add together is parts to whole. Now, bisector, the word bi means to sect. If you dissect, you cut it. So this is where we are going to cut exactly in half. It's a line, a segment, or ray, which cuts a segment or angle exactly in half. Two equal parts. So if you see the word bisector, you know you have equal parts. Now they might add together to make the whole. Parts to whole will still work. We always want the most specific information. And saying that two pieces are equal is more powerful than saying they add together to something bigger. So as a picture, it would look something like this. A, B, C, and D. If CD bisects AB, then, let's call this x in the middle, AX equals BX. Right? So bisector, though, the direction matters. The line, I don't know anything. This one, we'll look at some examples. This does the cutting. So a lot of times I draw fancy scissors. This is what gets cut in half. Okay, so be really careful with the direction of your bisector. If I'm looking at an angle, and let's call these P, Q, R, and S. So I would say if ray QR bisects angle PQS, then what I know is that these two are equal. Angle PQR is equal to angle RQS. And that would be by definition of bisector. So if I'm given bisector, then I can write the equation by the definition of bisector. Just as a quick review, you guys have had this formula before, the distance formula. We calculate the distance formula by taking the square root of the two x's subtracted and squared, and the two y's subtracted and squared. And for right now, if you want to leave it as a radical or if you want to work it out as an approximate decimal, either answer is fine. Midpoint formula, you've also had this before. This is where we take and we add the two x values and you divide by 2, and you add your two y values and divide by 2, and that gives you the xy of your midpoint. That's like an average. So the rest of this lesson is some examples about how to justify using these new properties. So if I give you this information, either in writing or in the picture, what can I conclude and by what reason? So what I know, if I know perpendicular and I see that box, the very next thing I want to write, what does the given give me? It gives me that angle CDA equals 90 degrees. And that happens by definition perpendicular. I could also write that angle CDB equals 90 degrees by definition perpendicular. Either one of those would be true. Now look at this next example. I'm going to skip number 2 a second. I'm going to go to number 3. I give you two intersecting lines. That's all it is. It's this picture right here. What true statements, what conclusion can you come up with? And there are actually 6 valid conclusions from this picture. Okay, so it just depends on where you're going with it, which one is better. But for right now, I could say that angle 1 is equal to angle 2 by vertical angles, because they are. I could also say that 3 and 4 are equal by the same reason. That's something I can assume from a picture. I also see that I have angles in pairs that make lines. So I could say that angle 3 plus angle 1 is equal to 180 by linear pair. And I could work my way all the way around, and I could say that angle 1 plus angle 4 is equal to 180 by linear pair. And I could say angle 4 plus angle 2 is equal to 180 by linear pair. And angle 2 plus angle 3 equals 180 by linear pair. In the very next example, we are going to look at number 2, 5, and 7, kind of out of order, but there's some important pieces that I want you to see by looking at those together.